Well, welcome back, everybody. Where I hope you enjoyed your break, and we are going to be blessed to learn about the hydroplate theory and the oceans. And we've got Matt Welborn. He's got a PhD in electrical engineering, and he works in the aerospace industry. And he's well suited to talk about the ocean because he used to live under it for months at a time, as being in the Navy. He was a nuclear trained submarine officer. And so, without any taking up any more time, here's Matt Welborn.
Thank you very much. I appreciate that introduction. Hopefully everybody can see me and hear me all right. Looks like the video is probably up, but
Yep,
if
looks
there's any
good.
problem, just let me know, but I'll just proceed. So anyway, as Brian said, I appreciate the intro, and I will be talking about the oceans today. And actually, one of the things I wanted to mention, and it reminded me that the fact that I was in the Navy, the ocean is just a huge place, and it's so dark and so big and so empty. Even though we think of it as teeming with life, it really is a huge place. And it reminded me when Ellen was talking about that earlier today about how the ocean was probably not part of God's original plan. So we're going to find out a little bit more today about what hydroplate theory says about our Earth's oceans. And as I go through this, I actually am going to have to acknowledge all of Dr. Walt Brown's work. A lot of the figures you'll see are probably familiar if you're familiar with some of his work. There's a few additional ones, but a lot of this material comes directly from his writings because it's so complete and so amazing. But I wanted to share a lot of it, put it in a form where I could share it. So the basic question I want to talk about is how can we account for the major features of our oceans? The oceans, as I talked about, are massive, and you see a slide, a picture there on the left-hand side that just shows part of the Pacific Basin, because this captures a lot of some of these major features that we're going to talk about during this talk today. So the oceans are extensive. They cover almost 3/4 of the Earth's surface. There's a lot of features like the mid-ocean ridges. We'll talk a little bit about that. Seamounts and table mounts, trenches, which are these amazing things that we don't even think about most of the time. They're thousands of miles long, very deep, very dark, and really amazing places. But it's very difficult to understand how they came to form and why they're part of the Earth's surface. And the hydroplate theory, I think, has a great explanation and really fits a lot of these evidence. We'll talk about some of these as we go through. We talked about basalt earlier. We heard about that and the Ring of Fire and submarine canyons, but I'll revisit some of those a little bit more detail as we go through the presentation today to talk about our oceans. Before I started, one of the things that helps me, I listened to the earlier talks and the introductory talk last night, and one of the things that I thought would be helpful is kind of like when I go to the mall and you go and look at the map and it says, "You are here." So this is a picture that I took out of the hydroplate theory book in the beginning, and I wanted to highlight some of the different topics in that picture of what happened during the flood to kind of show not only the parts that are related to the oceans that we'll hear about a little bit in this talk, but also how deeply they're related with some of the other portions of material that we're going to talk about. So you can see that this goes across the bottom as time, shows the different phases, the rupture phase, the flood phase, the continental drift phase. Some of these are quite short. The rupture was only 2 hours long. The flood phase was months long. We read about that in Genesis, obviously. And the continental drift phase was really short, about a day long. But that's where some of this stuff really starts to happen that formed our oceans. We'll talk about the Mid-Atlantic Ridge. Down in the lower left there, you see how the subsidence of the Pacific Plate and how the Atlantic Ocean formed in the Pacific Ocean. And there was rapid continental drift that moved things around. We'll talk about that a little bit. And then you see that during the later recovery phase, which we're still in today, is when other features of the ocean formed, but really that's kind of how our oceans formed and what we see the evidence of that, even as we see earthquakes and volcanoes still happening in these ocean areas, all of the groundwork was that for those processes was laid during this initial time when the oceans were formed. So again, I just wanted to show, you'll see some overlap with other topics. We'll talk a little bit about the inside of the earth and earthquakes and the crust and things like that. But part of it is because they're all related. They're all intimately linked as we talk about these different parts. So I thought that was helpful to kind of orient where we are. and I'll move on to kind of begin to talk about this. And I'm going to actually use the same approach that Walt used in his book, Dr. Brown used in his book, which is that we're going to contrast two different theories that exist to explain all the different evidences we'll see as we take a look at Earth's oceans. One of those theories is, of course, the hydroplate theory. And we just reviewed how there's 4 different phases of the hydroplate theory, from the rupture all the way through to the recovery today. And those phases are really what explain the catastrophic origin of our ocean features, the oceans themselves, and many of the features that are unique. And they occur only in certain places or certain parts of the ocean. And it's difficult to understand how they came to be, because in many ways we see things that don't exist on land. We see them deep in the oceans, and some of them we're still learning about. But it's really these 4 different phases and the different things that happen during those phases that we'll talk about as we go through it, and we explain over a series of these different features. I'll actually explain how the hydroplate theory handles all that evidence and fits it into a complete solution that describes the formations of the Earth's oceans and all their features. Now, the second theory that we're going to contrast with is plate tectonic theory. And you can see that I think you've heard a little bit about it, and I don't want to cover that theory too much, but I'm going to have a little bit of overview just so that we can see how there's 2 different sets of explanations that attempt to explain what we see in the Earth. So I have a picture there on the right-hand side that shows the different plates that are believed to exist under the plate tectonic theory. They're 30 to 60 miles thick. Some of them are actually quite large, they're as big as entire continents. Some of the plates are quite small. Some contain on top of these plates portions of oceans or just continents or a combination of both. And the idea behind the plate tectonic theory is that all these plates are moving relative to each other across the Earth's surface, and they're carrying the mountains and the continents and the oceans on top of them, and they're moving very slowly, so just a few centimeters or an inch or so per year. But that's kind of the conventional theory that's used to explain all these features. And as we go through the presentation, we'll take a look at all the work that Dr. Brown did to compare these 2 theories and show how really it's really not even close. But the hydroplate theory provides a much better explanation for all the features we see in the Earth's oceans. So I'm going to talk a little bit about the hydroplate theory to begin with. I'm going to talk about the 2 theories, the hydroplate and a little bit more about plate tectonics, and then we'll go into some of the specific evidences. And I thought I was glad that Ellen went earlier today and talked about some of the initial conditions that set up what we understand to be the hydroplate. And this slide really just focuses on one part of it. I'm not going to spend too much time, but it was really helpful. And this is going to be something I wanted to revisit in case people hadn't seen that in the earlier talk. But this is what happened. This is what the Earth looked like, at least part of it, before the flood. So there's several aspects shown here. There's this idea that there was a lower mantle, and between the mantle and the top layer, the Earth's crust, there was this subterranean water chamber. And the mantle itself was underneath everything and supported it, but the granite crust was above it. And in the granite crust, it was this 60-mile thick layer. It had water that was between the 2 layers. And up on top of the crust, there might have been mountains. There might have been pre-flood seas that were much smaller than today's oceans. But you can see that that's kind of the initial conditions of what we're going to talk about as the flood came and the rupture started and did all the activities that form today's oceans. And one of the things that you see there is this pillar-like structure where the 2 layers kind of touch together to support some of the overlying weight, but still it was this water chamber beneath that provided the source for a lot of the waters in our oceans. So I think that's kind of what we talked about. And of course, this water, because it's buried underneath this huge 60-mile thick layer of crust, was at very high pressures. And we'll see as we go through what happened as that was ruptured open and why that was the pressure that drove this out to form the oceans. This slide talks a little bit about the initial rupture. I'm going to kind of step through the hydroplate theory at a high level to just explain the parts that are relevant to the oceans. So the initial rupture, and I've got a couple pictures out of Dr. Brown's book that show both an everyday analogy, which is the idea of compressing a string with weights on top, and how that spring behaves. And then on the right-hand side of those images are the equivalent thing that happened as this rupture initially opened wide cracks in the Earth's surface that exposed that underlying subterranean water chamber and really started the rupture and the runaway process that created the oceans, that made the hydroplates move and created the Earth as we know today. So when this rupture initially happened, you can see that where a crack opened up on those top two images. And I think it's interesting to note on the right-hand side of that top row of pictures, that crack is very narrow at this point. And it's spreading rapidly all around the Earth. And we'll see that a little bit later. But it's interesting to note that that crack is 60 miles deep. That's as thick as these hydroplates are that's on top of the chamber. But as that crack ran all the way around the Earth, and we'll see some pictures later, it widened. And you can see that as we get to the middle row. That crack is widening and widening as the crumbling and erosion and the crust is being torn away by this water that's rushing out. And of course, the rushing water is not shown here, but we see effectively that crack is widening. So it's 60 miles deep, and now it's hundreds of miles wide. And as that happens, this is the thing that really tips the balance and creates this instability where on the lowest row, that spring rises up, the pressure forces it up, and it's the same thing that happened to the Earth's surface. You see the top of the mantle there is basically pushing up, splitting open, rising up into that empty spot that's created by the rupture and rising up above. And so we see that actually becomes the Atlantic floor. And we're going to see a little bit more of that as we go to the next slide. So here we'll see that the real story here is that before the flood, there was stability. And you can see in this picture on the left-hand side that we have two images. There's one that shows a stack of 60 miles thick of rock on top of this water chamber. And so you'd see there'd be high pressure, but essentially the pressure is balanced. 60 miles of rock sitting on top of the water chamber, and there's pressure, but it's completely balanced. The pressure of that water and rock on top is keeping everything balanced, even though it's 60 miles below the water or below the surface of the Earth. Now, when the flood's actually happening, that second column in the middle of the picture there shows that as that rupture opened up this huge opening, now we have 60 miles of water where there used to be rock. That rock is now gone, as you've heard from other parts of the hydroplate theory. It's been launched out, but now we have just water there. And because the water is much lighter, you see that it's no longer balanced. And that means that there's incredible pressure pushing up from below this chamber floor to push up. And you see the third section there is basically what it shows today. Today we're balanced again because those arrows, because that pressure weighing down from water is so much smaller, that ocean floor had to rise up, and it rose up all the way to form the much shallower ocean that we have today. The Atlantic Ocean is not 60 miles deep, right? It's thousands of feet on average, but we can see that ocean floor had to rise up to balance out those forces. And we'll see in the next slide how that rising and buckling mid-Atlantic ridge that sprang up, what happened both at the Atlantic Ocean as well as the other side of the Earth. And so this second picture, before we turn away, shows that inside of the Earth, at the top there, you see this Atlantic Ocean floor. And you see it's in red. It's kind of a representation of the same picture we saw, but now this is the top. The Atlantic Ocean is at the top, and we see Europe and Asia and Africa on one side. So we're looking down from the North Pole at the Atlantic Ocean on the top and the Pacific Ocean on the bottom. And what's happening is as that floor of the Atlantic Ocean rises up because it's no longer balanced in pressure, it actually looks like the entire center of the Earth is shifting. It has to shift towards the Atlantic Ocean. And this is the process that that was talked about in earlier presentations, where even just a small shift in all that inner rock that initially was solid, much of it was solid. It was not as hot as it is today. But when it shifts at those extremely high pressures, it melted a lot of that Earth, a lot of that outer core of the Earth melted. And not only did it shift a large part of all that rock and that solid inner core of the Earth towards the Atlantic floor. Remember that Atlantic floor rose up in that 60-mile void there. But the Pacific Ocean at the same time is being pulled up. And that's important. We'll see that as it's sucking that ocean floor up, it's pulling down these trenches, and the entire Pacific floor is subsiding. So that's kind of the high-level summary of how the hydroplate theory explains the initial formation of the oceans. Now, plate tectonics, I'll spend a slide or two on that just to help you understand what it is, and then we'll step through the individual evidences. So plate tectonics is widely known, textbooks, on the internet, videos in school, but a lot of them are actually fairly simplistic in my experience. There's a significant number of unanswered questions, and I think we'll have more talks this weekend that talk about how some of the things about plate tectonics theory that's really inadequate to explain the things we say. But here I want to focus on the oceans. And we talked about some of the key claims earlier. There's slow continental drift that takes place over long periods of time, hundreds of millions of years. There's the concept of seafloor spreading and plate subduction. We'll talk about that a little bit more as we go through. So here's kind of a little bit more of a picture that shows this idea behind plate tectonics. In plate tectonics, the idea is that it provides there has to be some mechanism that actually moves these plates, these thick 30 to 60 mile thick slabs of rock that drift across the surface of the earth. And one of the things that plate tectonics use to explain that is that there's convection currents. Even though the mantle, as we've heard before, is solid rock, it's crystalline rock, there's actually convection set up, much like in a boiling pot of water. But the idea now we have solid rock that very slowly, in some places it's warmer and it expands and rises up. And that you see at the top that makes a ridge. And at the same time, the idea is that somehow this convection would pull slabs apart. We saw those plates, these large plates, some as big as continents with mountains on top of them, but they're being essentially moved and pulled both by the force of density and changes in that, as well as somehow there must be some kind of friction that's pulling these plates apart, making ridges. And at the same time, on the other end of these slabs, they have to, one of them is somehow forced down. You see a picture here where one of them is forced down underneath another slab as they are sort of colliding. One of them has to dive down in order to allow the motion to continue. So this rising and descending rock inside of the mantle forms this current and drags the plates. So as we take a little bit closer look at what happens at these subduction zones, we saw this is the idea of plate tectonics and how they explain something. In particular, since we're looking at the ocean, we're going to focus on what made these extremely deep ocean trenches. And from a plate tectonics perspective, what they would say is that new crust forms at the ridges, but the old crust has to be consumed somewhere. So as these plates are either pushed or pulled along by drifting, or they're pulled down due to the density, these cold plates are somehow subducting down. One of them has sunk down and is diving down into the earth, this 60-mile thick slab of rock diving down into the earth underneath the second plate. And in their explanation, that's what causes the formation of these deep ocean trenches. Okay, and you can see in this picture, there's also other things that they use this idea to explain the idea of creation of magma because of friction and heat generation. Maybe there's volcanoes there, and we'll talk more about how this is their explanation for the Ring of Fire. But I wanted to just help you understand what these subduction zones are as we go forward. Okay, so now we've talked about we talked about the two theories, hydroplate theory and plate tectonic theory, but I wanted you to help you understand how Dr. Brown has really organized his discussion of oceans in his book in the beginning. And I've copied just part of the table over here, but you can see that he's got dozens of different, I'm only showing the part of the table. There's many more rows beneath this, but he goes through a whole series of different evidences that need explanations. And he compares side by side, how does hydroplate theory explain it, as opposed to how plate tectonics theory explains it. And the justification of this is how science is done. We have multiple theories to explain evidence. We go and we look at the evidence, we compare the facts, we come up with a mechanism, and we go and compare it and say, does the theory actually justify and explain the evidence that we see in the real world? So I think that's a great method to go through. We're going to step through, in the time that we have left, a few, maybe a dozen, half a dozen or so of these different concepts. I won't have time to go through all of them. And as I said, there's actually another dozen or so after this. But I'd invite you to ask questions or even pick up some of the materials. Go look in. It sounds like there's a digital version of the 9th edition of his book that's available. That's just fascinating. Huge amounts of information. Invite you to take a look at it. But one of the things I wanted to see before I leave this table is that there's actually a score for each one of these evidence. You see that under the hydroplate theory, it actually has green and yellow. That means it's well explained. The evidence itself, for example, the ring of fire, really fits well with the hydroplate theory, as opposed to if a category is scored as red, that means it has significant problems. And for example, you see that the plate tectonic theory really has problems explaining a lot of these different evidences that we see in the oceans themselves and in the other parts of the earth. So I'm going to take some time now to step through some of these, and we'll see what that looks like. So the first one is this idea of a ring of fire. The ring of fire you're probably familiar with, but it's really this ring of it includes not just the trenches, but it's basically a ring of hundreds of volcanoes that spans this horseshoe shape all around the Pacific Ocean. And if you hear about a volcano erupting, chances are it's in this place, because this is where 80% of the earthquakes and a vast number of the Earth's volcanoes are actually in this ring of fire. So it's thousands of miles long, and it's a concentration around the Pacific Basin that demonstrates that there's a lot of geothermal activity going on. And as we take a look, there's a couple bullets at the bottom there that kind of point to just a short description of how each one of the two theories that we're comparing, how does each one of these compare and explain the existence and the formation of the ring of fire. For the hydroplate theory, we see that the ring of fire actually marks the path of this great shearing. So we talked earlier about how the fact that when the Atlantic Ocean chamber floor rose up 60 miles, the entire Pacific Basin had to drop 30 miles. It basically dropped towards the center of the earth. The Pacific crust that was there, whatever land was there before, was broken up into many small pieces or larger pieces, but there was a shearing effect where that water got so deep and it began to fill in, because again, we had massive imbalance. But this ring of fire is basically the remains of that huge catastrophic event that created all these trenches around the outside of the Pacific plate there, as well as the residual volcanoes that remain. And we'll see a little bit more about that as we go forward. Now, that's the explanation of the hydroplate theory. The plate tectonics theory actually says that this ring of fire, as we saw in an earlier picture, is actually the place where plates are slowly moving inch by inch and diving down other plates that are there. And so it's actually these subduction zones that have created this ring of volcanoes. Now, one of the things that's pointed out is you see that this ring of fire actually has some interesting shapes. It's not straight lines as you would expect. It actually is what Walt has termed the arc and cusp shape. So you see there's lots of arcs, and we'll revisit this. But I just wanted to point out that there's some significant issues. And in fact, in his book, there's a huge amount of discussion about this. But really, it's this idea that plates are moving and creating these curved trenches and all kinds of volcanoes, both from the location of volcanoes, the shape of these trenches and everything, really does not fit the explanation that the plate tectonic theory gives for this particular feature. So another feature that's interesting that he talks about is what he calls gravity anomalies. Okay, I had a little bit of a battery computer power failure, so sorry about that. Anyway, we were finished talking about the ring of fire, and we began to talk about gravity anomalies. So this is another point of evidence that Walt talked about in his book. And one of the things that he pointed out, and this is an image from his book, it's a map that basically shows that using radar, they can measure the surface of the ocean. So the ocean sea level is not level, it's unlevel. And what this image shows is that at certain places, the surface of the ocean is actually much higher, and other places it's lower. And what accounts for that is the fact that gravity is actually different at different places. So you see, for example, that where gravity is extremely strong, it can pull the ocean, it can pull more water towards the land, towards the areas where the gravity is strong. And that would correspond to places where there's much denser rock or things like that. Now, one of the things that we see in this image is that along the ocean trenches that you see there in the Pacific, around the Pacific area, there's actually a deficiency of gravity. And so what that means is that there's not enough mass below the surface of the ocean. And when we do this analysis, they account for the shape of the surface of the
of the earth beneath it. But what that means is that there's actually less gravity there. It means that the trenches are actually not being pushed down, they're being pulled down. And one of the things about the hydroplate theory is that it's driven a lot by the force of gravity. That's the driving force. So the trenches themselves were being pulled down, and that actually matches the earlier theory we saw, the earlier aspects we saw where the whole Pacific Ocean itself was sucked down as the Atlantic floor was rising. And so the gravity anomalies actually reinforce that idea here. And the ocean trenches have these significant anomalies that we can even measure by satellite. I wanted to talk a little bit about the core mantle boundary and probably just go through this quickly. Ellen talked about this earlier, but one of the things I wanted to point out is that you see the oceans on top there, the Earth's crust and the mantle below that. Well, it's the Earth's core, the outer core there is actually melted. That's molten liquid, whereas the mantle itself is solid. And this is the same idea. And one of the things that really struck me as I was reading through and studying his theories is that the whole Earth has actually, and I think I heard this discussion last night, the whole Earth over the course of this catastrophic rupture and collapse, the Earth itself shrank as that whole outer core turned from solid into molten rock, into magma, because it has a higher density, it takes up less area, and you can see that it caused the entire Earth to collapse. And that's what formed, that's why the ocean basins exist, is the whole surface of the Earth has basically shrunken because the Earth has collapsed, especially at the Pacific Ocean floor. I do have a chart here that talks a little bit about these two types of rocks that we've been discussing. And one of the earlier talks about the initial condition talked about the fact that the entire Earth's crust at the beginning was granite. And you see the picture here that shows that granite is this lighter colored rock. It's primarily continental rock. It has different mineral composition, largely quartz and other things, but it has different mineral composition than basalt. So if you have basalt is what we actually found. This is the rock that commonly lies beneath our oceans below. And you'll see that we talked about the fact that as the Atlantic floor rose up and the Pacific basin basically subsided and was sucked up towards the inside of the Earth, it actually melted huge amounts of rock underneath the Earth's surface as there was huge shifting inside of the Earth, and it created massive amounts of magma that welled up and filled the floors of the ocean and created basalt. So that's why continental rock is so much different than basalt, than what's below the ocean floors. And this molten basalt spilled onto the chamber floors and created the ocean floors that we see today. Now, I think that this is actually a story that talks about the flood basalt. So the ocean itself, the Pacific Basin itself, we talked about the fact that it subsided. So massive amounts of melting occurred as this basalt rapidly rose up from the center of the Earth, from the outer core of the Earth, and through the mantle, and rose up and essentially flooded the basins, flooded the Pacific floor with molten magma that then condensed and formed this layer of thick basalt that could be miles thick. In fact, this is one of the areas where we really don't know much about it. There's some open questions about how thick that is, but one of the predictions from the hydroplate theory is that, remember, the Pacific, whatever crust was there before, sunk down many miles, perhaps 30 miles, magma welled up and filled the top of it over the top with basalt. And that created amazing features. It created the whole ocean floor. It created a vast amounts of sea mounts and table mounts that are over the floor of the Pacific. And I apologize, but I had a nice video that was taken from one of Brian Nichols' overview videos about the hydroplate theory. And he's done an amazing job. I'll just have to point you to it now, or it might be available that we could show later during the Q&A session or something like that. But there is a wonderful video that starts with this initial frame here and shows in an animated fashion how massive amounts of magma are rising out of the inside of the Earth and flooding the floor of the Pacific Ocean, forming the deep ocean trenches that ring this Pacific Ocean area. And it also formed tens of thousands of sea mounts and table mounts that are just difficult to explain in any other way, that are all over the bottom of the South Pacific Ocean. Massive amounts, tens of thousands of them, that are in some cases are miles high mountains on the bottom of the ocean floor that are basically come from magma upwelling and forming volcanoes on the bottom of the ocean floor. We talked a little bit about another point of evidence is the mid-ocean ridges, and there's been quite a bit of talk about that earlier. When the rupture occurred, the continental plates that existed at the time cracked open, and this high pressure water rushed out, and it actually tore open these wide gaps between the continental plates, and the chamber floors welled up and formed these ocean ridges. And you can see there's a little bit of a magnified version area there that shows on the Atlantic seafloor how there are these fracture zones, and there's also this cross hatching that shows that it actually was not a result of seafloor splitting in two dimensions or in two directions, east and west, but it actually was a full two-dimensional spreading as that whole seafloor rose up and formed these rifts. And I think I've got another chart here that shows a little bit more in detail here. So as the Atlantic floor and the mid-ocean ridge rose up, it stretched in two directions. It shows both these fracture zones and these rifts along the side, but it also has zones that cut across. And something like that just couldn't be explained by simple seafloor spreading caused by convection. So you see that three-dimensional image there that shows how ocean floor is rising up, making the mid-Atlantic ridge, and then you see the two continental plates there that are getting ready to spread across as they're going to ride down on that blanket of water and form the Atlantic Ocean and some of the other oceans where the continental plates receded away from this rising mid-ocean ridges. There's one point here I wanted to point out. There's this idea that was noticed by many scientists in the past, but one in particular was Bullard. And here is the idea, and this is, we've heard kind of in a couple references to this idea of Pangea, where there's this concept that there was one large continent, and many people have noticed that some of the continents on the Earth today fit together in sort of a jigsaw puzzle, where Africa and South America and North America kind of fit together. Well, one of the things that Dr. Brown's book points out is there's a number of distortions that have to happen to make this work. And I've listed the five there from his book, but basically Africa itself had to be shifted, and many other continents had to be shrunk by 35%, and many other continents actually had to rotate. So North America rotated clockwise and South America counterclockwise. Africa had to rotate in order to get this puzzle piece fit of these continents to fit this idea that's advanced by plate tectonics and this idea of Pangea. Whereas a much better fit is shown there on the right, where we see that the existing continents, including their continental shelves that extend out into the oceans, are a good fit with the existing mid-ocean ridges there. You see that much of the area was torn away, so there's still a gap that's missing. That's all the rock and the crustal material that was torn away and flung out as part of the rupture. But you see that it's a much better fit, especially we do it in 3 dimensions on that globe as is shown in that picture. And one final point of evidence I think that I wanted to talk about here before we wrap it up is this idea that we see a prediction by the hydroplate theory is that there will be continental material under the ocean floor. And so we talked about the idea that the whole Pacific crust, whatever land was there before this subsidence of the Pacific Ocean, basically sank many miles down towards the center of the Earth. And what that means is that if we had the ability to go down and look, we would find vast amounts of continental material, which was then buried. So it subsided, melted, and distorted much of the Pacific Ocean. But you see, because of that, all that magma came up and essentially paved the floor of the Pacific Ocean. But the result is that if we had the ability to go and look, the prediction by the hydroplate theory is that we would find large amounts of rock remaining from the original Pacific crust. And it turns out that, and I think somebody mentioned this in one of the earlier talks, that scientists have just recently realized that the country of New Zealand is actually part of a much larger submerged continent. So it's a large continent, meets all the requirements to be a continent, but it's 94% submerged. So the parts that we do see above the ocean level are the country of New Zealand, but also parts of that continent are 1,000 to several thousand feet deep. But much like other continents, it's made out of continental crust material. It has continental shelves, and it has only part of its land above water, and the rest is submerged below. So to me, it's amazing validation of some of the predictions of hydroplate theory. We see that there is continental material there, indicating that at one point in the past, that likely was the original surface of the Earth. And the same is likely true of other parts of the Pacific as we begin to continue to look for granite, which would have been the original crustal material down beneath the floor of the Pacific and Indian Oceans. Okay, I think I do have one final slide here before I wrap up, but there's one more point of evidence that I thought was interesting and has always impressed me from when I first began to look at these theories, and that's this idea of arc and cusp deformation in the ocean trenches. And I've kind of brought that same picture back we saw at the beginning here, which is that as you see these deep ocean trenches, thousands and thousands of feet deep, they're not straight lines, but they're in fact quite deep, but they're in the shape of arcs. And they're arcs that intercept in this cusp pattern. And I think, I'm not quite sure, but I suspect this might even be a cameo appearance by Dr. Brown here in this talk. I suspect that's his hand that's crushing one of those ping pong balls. But one of the experiments that he did to kind of illustrate this in his book is that he showed that if you take a sphere and you deform it, so much a ping pong ball is sort of like the surface of the Earth. It has a rigid outer shell. And if it gets deformed either by being pushed inward in the case of these ping pong balls, or in the case of Pacific Ocean, if there's a subsidence and there's a void and the crust is being sucked down, we would expect it to deform in this arc and cusp pattern, which is just an amazing fit with what we actually observe in the oceans. We have these deep trenches, thousands of miles long and thousands of feet deep, that form the same arc and cusp pattern around the rim of the Pacific. And that matches exactly what we would expect if this is in fact the explanation for the formation of the Pacific Ocean. And you see there in the picture again the things that we've talked about, the massive amounts of seamounts, the deep trenches, and the arc and cusp pattern of the different trenches as they ring around in this ring of fire around the Pacific Ocean. And really, this is the last slide here, but my final thoughts. The Earth's oceans really are a vast part of the planet. We talked about almost 3/4, and they have many features that are not present on the land. Many sea mountains that are huge, ocean trenches that are deep, these mid-ocean ridges, basalt that's in. It turns out there are these large basalt formations on the continental plates on the surface in Africa and India and the United States, but the ones under the ocean are many times larger. And that really reinforces this idea that basalt rose up from the molten earth inside the earth and came and paved the ocean floors. So the hydroplate theory provides a compelling explanation for this wide range of features. And one thing I just want to leave you with is it's based on this idea of gravity, something that really struck me as this catastrophic rupture occurred, that the gravity is the force that drove the whole earth to settle and realign. And that really is a common factor that we'll see later, I think, when others are going to talk about earthquakes and some of the other features that we see in the Earth's processes, is that gravity and the Earth settling and trying to stabilize it itself is really what explains a lot of the features that we see. So with that, I'm going to actually end my talk. Sorry for the interruption in the middle. Hopefully everybody still was able to see this, and I will actually be ready to answer questions if that's helpful.
Well, thank you. That was great. Excellent job. Excellent job. The question that pops to my mind is, do you have any idea how far the Pacific Ocean sank?
Yeah, so this was interesting. And I have to admit, when I originally read the theory, I read an earlier edition that talked about 10 miles. But with the revised theory that Dr. Brown had, because the crust was 60 miles thick, his estimate is that the Pacific Basin itself, in a very short period of time, sank 30 miles deep. So you can imagine that at some point, it would be like the mother of all potholes. The entire Pacific Ocean dropped 30 miles deep towards the center of the Earth. Whatever crust was there would have been broken up. We saw some of the remains of it in what is now known to be this continent of Zealandia that's largely submerged. But a lot of that 30 miles would then have settled out. Maybe it's stabilized. Lots of liquid magma came up and filled in that. And then over the thousands of years since that happened, there's been a lot of shifting of the Earth's land masses to fill in a lot of those gaps and try to stabilize the Earth. So it's an amazing thing to imagine. I can't imagine a hole that's 30 miles deep, but that kind of matches the numbers based on the fact that the Atlantic Ocean was initially 60 miles deep and the seafloor rose up to what it is today. At the same time, the Pacific Ocean got sucked in towards the center of the Earth, initially 30 miles deep.
Wow. Wow. And so, like, were the continents higher right after the flood, and then they sink down a little bit, and then the oceans rise up too? Would that be possible?
So it's interesting that you asked that. I mean, it's a fascinating question. What's happened is we talked about the fact that before the flood, there was this isostatic stability. So the pressure of the continents pushing down on the submerged, on this, the subterranean water chamber, and the mantle pushing up, all that balance was thrown out. And so since that time, we saw rapid shifting, continents moving. But what we see today, and I think this is a good point towards some of the later talks, is that even earthquakes today that we see are not caused by slowly drifting plates across the Earth's surface rubbing against each other. It's actually caused by the Earth trying to squeeze itself back into a stable position because of gravity. And that's what causes earthquakes today. And we see that as that happens, the Earth itself has shrunk. Its diameter has reduced, or I guess its radius has reduced by 180 miles. Wow. So the Earth is actually smaller than it was. That's what made it speed up so that we get 365 days in a year instead of 360. But the Earth sped up as it shrank, and the oceans themselves, everything settled out. So it sank 30 miles, but then a bunch of magma came and filled in and formed what we see today in the ocean floor, which in some places is 30,000 feet deep in some of the deepest trenches.
Oh, yeah. Yeah. And those earthquakes, they tend to go towards the trenches. Do I understand that right, too?
Yeah, that's right. So both of the theories, hydroplate theory and plate tectonics, have explanations for earthquakes. We saw that plate tectonics tries to say that it's these slowly shifting things. You've heard of the San Andreas Fault and all these things. But it turns out that these earthquakes actually match exactly where the hydroplate theory would predict, that most of the earthquakes are focused on the Earth around the Ring of Fire. If you've heard about Fukushima, or if you heard about earthquakes in Indonesia or the Philippines that cause tidal waves, that's where most of the earthquake activity in the U.S. is. I mean, thankfully, North Carolina, we don't get too many earthquakes where I live, but California does, right? So we always laugh about California falling into the Pacific someday. Well, I don't know, maybe. But it's basically the Earth trying to get itself back into a stable position. As, in fact, there's some interesting pictures in the book that show every time the earthquake occurs, or as surface portions of the Earth actually slowly shift, it's almost like they're being sucked towards the Pacific area. And there's an interesting picture in the book, I'm not sure if we'll see it this weekend, where they can track with GPS now as the surface of the Earth moves. It's all sort of creeping towards the Pacific to try to balance out these deficiencies that still exist in the Pacific Ocean.
Okay. And guy asked, where'd all the water go after the flood?
Yeah, so that's a good question. Where did all the water go? I think one of the things that we heard earlier is that at the beginning of the flood, the mountains that existed on the Earth that were covered by the flood, that's what we read in Genesis. All the mountains of the Earth were covered. They were submerged by water. Well, at that point, it turns out that even if you took all the water today that's in Earth's oceans, and if you leveled out all the seas and the mountains, that would be enough water to submerge the entire Earth by 9,000 feet deep. So the answer is that all the water is still here. It's just that what has happened is that these ocean basins have opened up, all the water drained off the continents after the flood and has filled in our oceans. But the oceans are much deeper. They were actually much deeper at one point, and they're shallower than they were. But the oceans hold all the water in the Atlantic Ocean, the Pacific Ocean, the Indian Ocean. That's the water that at one point completely covered all the mountains of the earth. And as the earth's crust was shifting, the hydroplates were moving, and these ocean basins were subsiding and rising up. Where it settled out is what the world looks like today, with the 7 continents, the 8 continents now that we have poking up above the earth. But that's what remains, and all the water has retreated into the ocean basins that actually cover almost 3/4 of the Earth's surface.
Right, especially the Pacific that got sucked in. You showed that graph that compared two theories. Is there a graph like that that contrasts the Ring of Fire and earthquakes and stuff that show that HPT is the best explanation?
Oh yeah, in fact, I mean, I didn't want to go too much into that. I think there might even be a talk later this weekend. I'm not sure about the agenda that talks about earthquakes, but there's and there's actually almost many pages of this in Dr. Brown's book in the beginning. He's done extensive work, but we saw just some of the summary statistic there, that the vast amount of volcanic and earthquake activity is all around that Pacific basin in the Ring of Fire. And we saw the hydroplate explanation. And in his book, he actually talks about the explanation that plate tectonics tries to provide for the existence of the Ring of Fire and all these subduction zones that they claim are the explanation for the ocean trenches. But really, there's a lot of problems with that, dozens of different points of evidence and ways that theory just doesn't fit what you'd expect for the deep trenches that form this Ring of Fire in the Pacific Ocean trench region.
Another question. You said that the liquid core shrank, and did the mass stay the same for the Earth then, even though it was denser inside?
Well, that's a good question, and I think one of the earlier talks talked about the fact that the theory has actually been revised as we've learned more about it. So if you think about all the original mass of the Earth, some of it, according to the hydroplate theory, left the Earth. So some of that mass makes up the asteroids, makes up the trans-Neptunian objects, makes up meteorites and comets that circle in our solar system. But the vast majority of it obviously stayed on the Earth. So there was torrential rain that came down. A lot of that water was ejected out and went up into the air and fell down as rain and mud and hail and rocks. There was vast amounts of sediments that came out and created in some places, thousands of feet thick of sedimentary rock, but most of the mass stayed here. It's just that when that inner core, that inner core of the Earth is solid, the outer core is what has turned into magma. So it's liquid. And when it melted, because of all the activity and the heat generated by friction and settling, it actually contracted. And that's what made the Earth shrink. Hundreds of miles smaller than it was before the flood.
There's some really good questions here. This is our 10-minute break. So if people in the audience want to get up and walk around, they certainly can. But if you don't mind answering one more,
sure, I'll be glad to.
The crossover depth. The guy asked if you could give it about the crossover depth, 220 miles down, how something gets molten and then it keeps sinking instead of going up.
Sure. And this is one of the things that makes a lot of sense to me. I learned about the crossover depth only recently. I was reading about plate tectonics and about the hydroplate theory. And the point that he mentions, this idea of a crossover depth, is that as you go down below the Earth's surface, when you get down about 220 miles, the pressure gets higher and higher, obviously, because when you're that far down, you have 220 miles of rock above you. But at that pressure, what happens is at this crossover depth, if rock were to melt, if it turns into magma, it turns out that rock is rigid and it has the same density even if you put it under pressure. But at some point when it melts because of heat, magma itself can actually contract. So although rock doesn't contract, magma contracts. And at those pressures, when you get down 220 miles, it's actually the case that the magma is more dense. And so if rock were to melt at that point, it actually wants to drain down towards the center of the Earth, towards the inner core, the outer core of the Earth. Whereas if it's above the crossover depth, that magma is less dense and it actually wants to try to rise up towards the Earth's surface. So that's why a lot of the magma that we see that comes out of volcanoes must have been formed close to the surface of the Earth above the crossover depth. If there's magma below the crossover depth, it wants to descend down towards the outer core of the Earth. And that's why basically what has happened is any kind of magma that's formed in the mantle below 220 miles, it will seek out cracks and crevices, and it will try to drain down towards the inner core of the earth because it's more dense, kind of like water running down a drain. It'll try to go down the drain. And that's why you see the outer core is liquid magma, whereas the mantle stays solid and crystalline and supports everything on top of it. In fact, it's interesting. I was looking at the theory says that the Earth itself is 180 miles smaller than it was before. Well,
Wow.
it turns out that if the rest of the mantle continued to melt over time, if there were more heat, the Earth would continue to crack or to contract, and it would get even smaller, even by hundreds of more miles, which is kind of a scary thought. Imagine what it would be like on the surface of the Earth if the Earth started to shrink another 100 or a few hundred miles, and you're not inside of an arc. You're going to be in big trouble, right?
Thank you very much.